Hello, and welcome to Regression Analysis in SAS by me, Dr. Alan Brain. This course covers simple linear regression, multilinear regression, categorical variables in multilinear regression, and logistic regression. This course does not cover the theory. The files for this course are available on drbrainstats.com, and you can download the zip file. As we're not going to bother with the theory, we can go straight into an example for the simple linear regression. In a sale of new cars, it's generally the case that the more expensive a car, the greater the profit for the dealer. The sales manager wants to help the salespersons make the most profitable sales possible to each customer. One particular area of interest is the amount of credit successfully applied for new car purchases. The manager has obtained a sample of 30 recently completed car sales where the customer secured a credit loan. The dataset Reg01 contains two variables: gross annual income of the purchases in thousands, and Y, the amount of credit loan obtained by the purchaser. It'd be clearly helpful for a salesperson to know how much credit a potential purchaser can apply for, given the knowledge of their income. So within SAS, we're going to create a simple linear regression. And this is our solution. I won't be reading out code because I know it's boring. Instead, I will be explaining it. So first of all, we need to see it's got procreg. That is the SAS procedure to use. The next is model y equals x. Model's command y equals x tells you want to predict y using x. And finally, we got the run and quit. Without the quit statement, the procedure will not stop running. And these are our results. We are interested in the parameter estimates box, where it tells us our model scores. Using the equation y equals mx plus c, we can see the intercept is 3.43, and we need to multiply SARI by 0.19558 to get our predicted credit. Now we need to know whether these variables are strong enough to use in a model. Using the t statistic, we can see if they're both below 0.05. So how do we know if a model is any good? The measurement used for simple linear regression is r squared. R squared is a fraction between 0 and 1, and it has no units. If we have an r squared below 0.7, we should question whether there is a relationship between the variables. So now we can look at our results again, and we see that the r squared value is greater than 0.7. So we can use these results with confidence. So, as an example, if someone asked us how much credit should we give somebody whose salary is 30,000, as our data is in the thousands, we would need to amend our x value to 30. So using our ymx plus c, we apply the 30 into the equation, and we know that the credit offered should be 9,300. With simple linear regression finished, we are now going to start multiple linear regression. It's a rare occurrence when we can use only one variable to predict an outcome with confidence. When we use more than one explanatory variable to predict the outcome, we call this multiple linear regression, as shown on the equation on the slide, where y is the dependent, c is the intercept, n, p, x, p are the independent explanatory variables, and e the error term. When developer models, the error term value is very close to 0, so we tend to ignore it. This is only here for accuracy and won't be considered further on. Before we start our next example, we need to consider the measurement. In multiple regression models, the R-squared will increase as more variables are included in the model. Therefore, we will need to use the adjusted R-square. So, example of a multilinear regression. A CSV file called multi1 contains values of the following variables for a sample of 19 companies. Our first example involves constructing a multiple linear regression model to predict PER from profit and growth. As we can see from the solution, it is very similar to our simple linear regression code, apart from now, instead of having one variable, we have two: profit, growth. And these are our results. Using the estimates, the multiple linear regression equation is predicted PR 5.56, which is the intercept, plus 0.47 times profit plus 0.2 times growth. As this equation uses two explanatory variables, we have to use the adjusted R square for its performance. With an adjusted R square of 0.54, we may consider not using this model as it falls under the 0.7 mark. But if we lack an alternative model, then we'd have to use it. And so we start our second example of multilinear regression. A CSV file called multi2 contains the first order of drinks consumed in a restaurant or bar based on the first 31 days. Now we want to construct a multiple linear regression model to predict Y, for drinks remaining, from the average price of drink ordered, and the average daytime temperature. And this is our solution end results. The code should look very familiar, and understanding the results should be straightforward. And with adjustment R squared of 0.68, this is a very close value to 0.7, so we could consider using this model with confidence. If we looked into our results further, we notice that the variable x1, the average price of a drink, has a t-statistic greater than 0.05. This tells us that this variable is weak within the model, so we need to model again without the variable x1, which gives us our whole new model. And if you notice, by dropping this weak variable, the adjusted R square has not reduced significantly either. It has gone from 0.68 to 0.68. Sequential approaches. Variable selection techniques tend to cause arguments among data scientists and statisticians, which I will not delve into here. There are always people dismissing procedures no matter what field you're in. I only mention this so that you're aware of this argument. There are three main sequential approaches: forwards, backwards, and stepwise. Examples of these are available in the book. Categorical variables in a regression model. The dataset categ2 relates to the sales of number of cakes from a certain franchise. The variables of interest are number of households in the region, number of cake sales, and a location. Now we want to predict sales from location and households using PROC-GLM. So we've now moved from using PROC-Reg to PROC-GLM. PROC-GLM is a procedure used as it allows us to use categorical variables to predict a linear target. Now class, this tells SAS that the variables to follow are the categorical ones. SS3 requests the output type 3 sum square. This provides the F statistic that tells us if the variable is predictive or not. And solution. This tells SAS to produce the parameter estimates. Which brings us to our results. With the categorical variable included, each bin has been given its own score. Unlike continuous variables, where we multiply the explanatory variable by the estimates, for categorical, they have a fixed value. So this is our equations. Completing equations above, we'll find for shops located in malls, location 2, to enter highest mean sales as it produces the highest value. And now, logistic regression. Logistic regression is used to calculate the probability of an event occurring. For example, a person responded to a direct mail campaign, or a customer defaulted on a loan. When considering a logistic regression, we need to add up the model scores, then convert it into a probability, as will be demonstrated. So in this exercise, we'll be using a file called Logistic1. This file has a binary response variable called sold, which is equal to 1 if a sale has been made, and 0 otherwise. There are three predictor variables: income, mortgage, and tier. The variable tier takes on values 1 to 4. Tiers with a rank of 1 have the highest prestige, while those with 4 have the lowest. And this is our solution. As you can see, the code looks very similar. Our procedure is PROC-Logistic. Our data, perm logistic1, but this time we've got an option called descending. This tells SAS that we're modeling 1s instead of 0. Class, that's for our categorical variables. Param equals ref, that tells SAS to produce our coefficients. And model statement, what we want to predict and with what variables. and these are our results. We could treat the p-archive-squared values as it did with a t-statistic. So our equation is as shown, but we have to convert this score into a probability. So if we're translating the results, as before, we'll score up the model, which is quite straightforward, by using ID1. And then with our score, we can convert that into a probability, as shown on the slide. So the probability of a sale for ID1 is 17.26%. This brings us an end to an introduction of regression techniques using SAS. SAS allows you to hash the predictor scores of different data sets as demonstrated in the book. This presentation focused on creating the scores and understanding the results. Thank you. Additional material is available in a reasonably priced book available on Amazon.